These candy bars are mass-produced at a scale that's almost unbelievable. Reese's, Mars, and Snickers are created by the millions inside roaring factories using molten chocolate, robotic precision, and non-stop production lines. In this video, we're going deep inside the process to show you how these legendary sweets are really made. Reese's peanut butter cups begin with the bulk delivery of raw peanuts to the factory's intake silos, where they are gravity-fed into the initial sorting system. These peanuts are inspected mechanically, using a combination of vibrating sieves and optical sorters to remove any debris, underdeveloped kernels, or foreign materials. Once sorted, the peanuts move via enclosed conveyors to massive gas-fired rotary roasters. These roasters tumble the peanuts at temperatures ranging from 160 to 180 degrees Celsius for up to 30 minutes, depending on the batch specifications. Uniform roasting is critical, as it directly impacts the flavor profile of the peanut butter core. Immediately after roasting, the peanuts are dropped into rapid cooling bins to halt the cooking process. Once cooled, they're transported to a dry deskinning machine, where rubber-lined rollers strip the outer skins, which are then removed via airflow separators. The cleaned roasted peanuts are directed into hoppers that feed them into industrial grinders. The first stage produces a coarse paste, while the second stage refines this paste into a smooth, semi-solid mass with just enough texture to give Reese's its signature, slightly grainy peanut butter. At this stage, the peanut paste is blended with dextrose, salt, and a small quantity of vegetable oil stabilizers in jacketed mixing tanks. These tanks are equipped with high-torque agitators that ensure uniform mixing and prevent separation. The peanut butter is then pumped into storage tanks held at a steady 40 degrees Celsius to maintain pourability, with recirculation loops preventing oil separation. While the peanut butter is being prepared, the chocolate coating is simultaneously processed in a different section of the plant. Solid chocolate blocks arrive in insulated pallets and are broken down into manageable chunks by automated crushers. These chunks are melted in conical tempering kettles, where the chocolate is cycled through precise temperature phases. Heating to 45 degrees Celsius to dissolve fat crystals, cooling to 27 degrees Celsius to encourage type 5 crystal formation, and then reheating slightly to 30 to 31 degrees Celsius to prepare for molding. This tempered chocolate is fed through stainless steel piping with heated jackets into the deposition zone. The chocolate is deposited into paper-lined plastic molds using servo-controlled nozzles. The molds are pre-fitted with pleated paper cups, automatically dispensed and placed by robotic arms. The bottom layer of chocolate is dispensed in a circular motion to form a consistent base. The molds are gently vibrated on a plate to spread the chocolate evenly and eliminate air bubbles. Once the bottom shell is semi-set, the peanut butter is deposited in the center using another set of volumetric piston fillers. Each dollop is carefully controlled to ensure it stays centered and does not bleed into the side walls, which would prevent the top chocolate layer from sealing properly. The peanut butter is slightly cooler than the chocolate to preserve its form as it's deposited. The top chocolate layer is applied almost immediately after the peanut butter centers are deposited. Another set of nozzles applies tempered chocolate to fully enrobe the filling, again followed by brief vibration to ensure complete coverage and smooth surface finish. This layered structure of chocolate, peanut butter, and chocolate is the signature of every Reese's cup, and the volumes are calibrated down to the milliliter. Next, the filled molds enter a tiered cooling tunnel. This tunnel is divided into climate zones, with each zone dropping in temperature by small increments, from 20 degrees Celsius down to around 8 degrees Celsius, over the course of 15 to 18 minutes. This gradual cooling prevents thermal shock, which could cause cracking or separation between the chocolate and filling. Each zone is equipped with air circulation fans, refrigeration coils, and humidity control systems to ensure perfect crystallization of the chocolate. After the cooling process is complete, the now fully formed Reese's cups are ejected from their molds using a pneumatic plunger system that pushes from beneath the mold cavities. The cups remain in their paper liners and are transferred to conveyance lanes for wrapping. At this point, the cups are still exposed and vulnerable to environmental conditions, so the transfer occurs within a controlled, filtered air enclosure to prevent contamination. The wrapping process uses horizontal flow wrappers. Each Reese's cup is aligned via guide rails and funneled into individual wrapping lanes. Printed foil is unwound from rolls and cut to size by rotary knives. The cup is pushed onto the foil by a mechanical arm, and the foil is folded and sealed around the candy using heat-sealing jaws that close in fractions of a second. The wrapped cups are then printed with batch codes and expiration dates using inkjet or thermal printers. For king-size or multi-cup packages, the single wrapped cups are automatically grouped and loaded into larger overwrap film using a secondary wrapping machine. These packages are then loaded into display cartons by robotic pick-and-place arms that orient each unit for retail presentation. These cartons are glued or tab-sealed, then labeled with product identifiers, shipping information, and QR codes for traceability. Before packaging is finalized, random samples are pulled from each production batch and sent to quality assurance labs. Here, technicians weigh each cup, examine chocolate gloss and thickness under calibrated lighting, and use penetrometers to test the firmness of the peanut butter. They also cut cross-sections of the cups to visually inspect layering uniformity and check for air gaps or structural flaws. Once cleared, finished cartons are palletized using robotic stacking systems that build stable load units based on truck optimization software. Each pallet is stretch wrapped and labeled with RFID tags that track its origin, contents, and destination. These pallets are loaded onto climate-controlled trucks that maintain the cargo area between 10 degrees Celsius and 22 degrees Celsius, preventing chocolate bloom or melting during transport. Even after the cups leave the factory, Hershey maintains control over their handling through advanced logistics software. This platform integrates sales forecasts, retailer data, and shipping conditions to prioritize inventory rotation and ensure that product closest to expiration is delivered first. Warehouses use automated pick systems and real-time barcode scanning to manage stock. In addition to the standard production line, seasonal Reese's cups, like pumpkin or heart shapes, are produced using interchangeable mold plates. These specialty shapes require adjustments in chocolate and filling deposition to accommodate varied volume and geometry. The same precision is applied to these runs, though the visual inspection is even more rigorous due to complex shapes. Flavor innovation is handled through a separate R&D pipeline. Variants like white chocolate or dark chocolate cups require their own tempering parameters and material handling systems to prevent cross-contamination. These are produced in small trial batches on modular production lines until formulations are approved for full-scale production. From a sustainability perspective, Hershey continuously works to reduce energy and material waste. Chocolate tempering kettles use thermal recirculation systems to recover heat energy, while the roasting exhaust is captured and scrubbed for reuse in preheating systems. All peanut skins, chocolate trimmings, and off-spec cups are collected and either reprocessed or converted into animal feed and energy through biodigesters. This entire system, roasting, grinding, tempering, depositing, cooling, wrapping, inspecting, and shipping, operates in a tightly synchronized loop, monitored by real-time factory control software. Supervisors can access dashboards showing throughput, downtime, temperature profiles, and ingredient usage. Alerts notify operators of any deviations from specification, and corrective actions are logged for traceability. Every Reese's cup, whether it's a classic 2-pack or a seasonal novelty, is the result of layered processes fine-tuned to deliver the exact same flavor and texture every time. From the precise ratio of peanut to salt, to the sheen on the chocolate, to the shape of the paper liner, all of it is the product of exacting industrial craftsmanship. Mars chocolate bar production starts with the arrival of key ingredients at the facility: raw cocoa mass, cocoa butter, sugar, skimmed milk powder, lactose, glucose syrup, and proteins used in the nougat layer. All ingredients are subject to strict quality control before entering the production line. Cocoa mass and butter are delivered in solid block form, stored in climate-controlled zones, and tested for fat content, aroma, and particle size. Sugar arrives in bulk and is transferred pneumatically into silos. Milk powders are delivered in sealed containers, sampled for moisture and purity, then funneled to automated dosing stations. The chocolate phase begins with tempering and mixing. Cocoa mass and cocoa butter are first melted in stainless steel, jacketed tanks at precise temperature ranges, typically between 45 degrees Celsius to 50 degrees Celsius. This molten chocolate mixture is sent into high-capacity blenders, where sugar, milk powders, and lactose are added. The mixing process creates a coarse paste which then undergoes refining. Refining is done using 5-roll refiners, massive machines where the chocolate paste passes through a series of increasingly narrow steel rollers. These rollers compress the paste down to a fine particle size between 20 to 30 microns. This size range ensures that the final chocolate feels silky and not gritty. Sensors monitor the output continuously for particle size and adjust roller pressure accordingly. The refined paste is moved into conching machines, where it's heated and agitated for several hours. Conching removes volatile acids and moisture while developing flavor and viscosity. Emulsifiers like soy lecithin are added during this phase to control flow behavior. The conched chocolate is then pumped into holding tanks kept at 30 to 32 degrees Celsius, ready for use in bar coating and mold filling. In parallel, the nougat layer is being produced in a different section of the factory. Mars's nougat starts by mixing sugar, glucose syrup, and water in large cookers. This mixture is heated to form a syrup, which is transferred to industrial aerators. Here, whipped protein, often derived from egg whites or hydrolyzed soy protein, is added. The high-speed aerators incorporate air into the mix, giving nougat its light, chewy texture. Once whipped, the nougat is enriched with milk powder, fats, and flavoring components to build creaminess and mouthfeel. The warm, aerated nougat is extruded onto a continuously moving conveyor belt as a wide, flat slab. As it travels down the line, it is cooled by overhead airflow units to partially set its structure. Once firm enough, the nougat sheet is trimmed to a uniform width using high-speed rotary blades and moves to the caramel deposition stage. Mars caramel is produced using continuous vacuum cookers. Sugar, glucose syrup, and milk ingredients are heated under vacuum to lower the boiling point, preserving soft texture and rich dairy flavor. Once the caramel reaches the desired consistency, it is deposited as a thin, even layer over the traveling nougat base. This layered slab now resembles the cross-section of a Mars bar before chocolate coating. Cooling tunnels set the caramel onto the nougat layer using a staged drop in temperature from ambient to around 10 to 12 degrees Celsius. Once the slab is fully set, it moves to ultrasonic cutters. These high-frequency blades cut the slab into bar-length segments with minimal compression, maintaining clean edges and uniform size. Each bar now contains a core of structured nougat and a top layer of soft caramel, and is ready for chocolate coating. The next stop is the enrobing line. Each bar is placed onto a perforated conveyor belt and passes through a chocolate curtain, molten tempered chocolate falling in a continuous sheet. A bottoming roller ensures the underside is coated first. Air knives blow off excess chocolate and shape the final bar profile. Edge trimming guides ensure the sides are evenly coated without pooling. The entire chocolate coating process is conducted at controlled temperatures, usually around 30 degrees Celsius, to maintain chocolate viscosity and gloss. Once coated, the bars enter a long, refrigerated cooling tunnel. This tunnel gradually lowers the temperature over multiple zones, ensuring that the chocolate sets smoothly without cracks or bloom. Cooling takes roughly 12 to 15 minutes. Humidity is strictly controlled throughout to prevent condensation on the bars. Upon exiting the cooling tunnel, the bars are transferred to the wrapping station. Each bar is aligned into feeding lanes and enters a horizontal flow wrapper. Printed packaging film is unwound and formed around each bar. The wrapper is sealed using heat and pressure at the ends and along the back. Prior to sealing, the package interior may be flushed with nitrogen gas to remove oxygen and extend shelf life. Barcodes, batch codes, and expiry dates are printed in real time using high-speed inkjet printers. Cameras verify print legibility and seal integrity, and any faulty packages are ejected from the line. Accepted bars are automatically grouped into cartons, 12, 24, or 36 count configurations, depending on destination and retail requirements. Cartons are sealed with glue or interlocking flaps and labeled with destination codes. Palletizing robots stack cartons onto wooden or plastic pallets using algorithms that maximize load stability and cube efficiency. Once stacked, the pallets are stretch wrapped with plastic film and labeled with RFID tags containing tracking and batch data. These pallets are transported via forklifts or automated guided vehicles to temperature-controlled storage areas. Inventory management systems track product age and availability in real time. Orders are picked and dispatched using a just-in-time system integrated with retailer demand signals and distribution schedules. In addition to core Mars bars, the same line can be configured to produce variations such as fun size, twin pack, or regional editions. Changeovers involve switching cutting equipment, recalibrating depositor heads, and swapping packaging materials. This flexibility allows Mars to meet seasonal demand spikes or promotional formats without building entirely new production lines. Throughout the process, dozens of sensors, cameras, and feedback systems maintain quality. Chocolate viscosity is tracked with inline viscometers. Weight checks are performed on each bar using precision scales, and metal detectors ensure product safety. Quality control technicians also pull random samples hourly to inspect cross-sections, flavor, and mouthfeel. Sensory testing panels taste test bars daily to ensure consistency. Waste is minimized through rework systems. Off-spec nougat and caramel are reprocessed when possible, and chocolate trimmings are collected and remelted for future batches. Scraps unsuitable for reuse are converted to animal feed or processed through waste-to-energy systems. Sustainability initiatives have also taken hold. Mars uses responsibly sourced cocoa certified by third-party organizations and invests in water reduction systems and energy recovery technology in its factories. Packaging material is being reformulated for recyclability and reduced plastic usage. Each Mars bar, though it appears simple, is the product of a deeply engineered process, combining food chemistry, automated manufacturing, and strict quality assurance to ensure uniformity on a scale of millions of units per day. From raw cocoa mass to wrapped bar, the journey is a marvel of food industry precision. Snickers bars begin their life in a highly coordinated manufacturing facility where precision equipment, food science, and industrial engineering merge to produce one of the world's most popular candy bars. The process starts at the very foundation, the peanuts. Whole, raw peanuts arrive at the factory in food-grade bulk containers or via pneumatic tankers. These nuts are funneled into intake hoppers equipped with vibrating screens and magnets to remove stones, shells, or metal fragments. From there, they're transferred to silos with humidity and temperature controls, where they await roasting. The roasting process is crucial in developing the Snickers bar's signature crunch and roasted aroma. The peanuts are moved from silos into rotary drum roasters, which tumble them continuously at temperatures between 160 to 180 degrees Celsius. The roasting cycle is tightly timed, usually around 20 to 25 minutes, and computer systems monitor kernel temperature, moisture release, and color development using near-infrared sensors. Once roasting is complete, the peanuts are transferred to a cooling conveyor where chilled, filtered air rapidly reduces the kernel temperature, halting the cooking process and preserving the ideal crunch. After cooling, the peanuts are split into two processing streams. A portion is designated for whole peanut inclusion. These go through size grading systems and optical sorters that scan for broken or discolored nuts. Defective peanuts are automatically removed with precise puffs of air. The selected whole peanuts are sent to temporary storage hoppers until they are needed at the assembly stage. The other stream is milled into granulated peanut fragments. The peanuts pass through precision grinders that can be adjusted to produce different textures, from coarse granules to fine peanut meal. These different textures are essential as the coarse fragments are used in the caramel mixture for crunch, while the finer ones enhance the nutty flavor in the nougat. While the peanuts are being processed, the nougat, a critical layer in every Snickers bar, is produced in an adjacent line. The nougat base is made by mixing glucose syrup, sugar, powdered milk, and a whipped protein sauce, typically egg whites or hydrolyzed soy protein, isolate. These ingredients are heated in a batch cooker where sugar and glucose syrup dissolve and are cooked to a specific temperature to ensure the right consistency. The hot syrup is pumped into an aeration chamber where it's rapidly whipped to incorporate micro bubbles of air, turning the dense syrup into a light, chewy base. To this base, ground peanut meal and sometimes cocoa powder are added, depending on the variation of Snickers being produced. The aerated nougat mixture is deposited onto a moving steel conveyor belt in a uniform slab, usually about 10 to 15 millimeters thick. The slab is leveled with motorized spreaders to ensure consistency in thickness, and then it enters a cooling tunnel. The tunnel gradually brings down the temperature of the nougat slab using fans and chilled air, solidifying the structure just enough for it to carry additional layers without collapsing. The next step is caramel preparation. Caramel for Snickers is not a generic mixture. It's custom designed for the brand's chewy, stretchy mouthfeel. It begins with a combination of glucose syrup, sugar, milk solids, and butter, cooked under vacuum to reduce the boiling point and develop flavor while maintaining softness. This caramel is cooked in large, continuous cookers that can process hundreds of liters per hour. The caramel is cooled slightly and mixed with coarse ground peanuts, creating the crunchy, rich upper layer of the bar. This hot caramel peanut mixture is deposited directly onto the cooled nougat slab. The deposition system includes a manifold that spreads the mixture evenly across the slab, forming a second layer. This dual-layered slab continues down the production line into another cooling tunnel, where the caramel firms up without hardening completely, remaining flexible for cutting. Once sufficiently cooled, the dual-layer slab is transported to the guillotine cutter. Using ultrasonic or hot wire blades, the slab is cut into bar-width strips and then into individual bar lengths, usually 50 to 60 grams each. These bars are then conveyed into the enrobing line, where they receive their final layer, chocolate. The chocolate coating used on Snickers bars is made in-house, using a proprietary blend of cocoa mass, cocoa butter, sugar, and milk powders. These ingredients are refined and conched in large machines that heat, mix, and aerate the chocolate to develop flavor and reduce particle size. The finished chocolate is held in jacketed tanks at a precisely controlled temperature of 30 to 32 degrees Celsius, ready for tempering. Tempering involves carefully controlling the crystallization of cocoa butter to ensure that the final chocolate has the right snap, gloss, and shelf stability. The tempered chocolate is pumped into enrobing machines, long tunnels, where a curtain of liquid chocolate coats the bars as they move along a mesh conveyor. A bottoming wheel applies chocolate to the underside of each bar, ensuring full coverage. Excess chocolate is removed using air knives, and the bars are passed under vibrating plates to level the coating. The coated bars are conveyed into a cooling tunnel approximately 20 to 30 meters long. The temperature in the tunnel drops from room temperature to about 8 to 10 degrees Celsius in graduated steps. This controlled cooling sets the chocolate without causing bloom or shrinkage. By the time the bars emerge, they are fully formed and ready for packaging. Each Snickers bar is picked up by robotic arms and placed into horizontal flow wrapping machines. Printed packaging film is formed around the bar, sealed at both ends and along the back using heat sealing jaws. The sealed bars are printed with a batch number, expiry date, and traceability code. Optical scanners inspect each package for proper seal integrity, print clarity, and alignment. The wrapped bars are grouped into cartons using high-speed collation systems. Depending on the SKU, bars may be packed into boxes of 12, 24, or 48 units. The cartons are sealed, labeled with logistics and traceability data, and palletized by robotic stacking systems. Pallets are shrink-wrapped and moved to staging areas for shipment. Throughout this entire process, quality assurance plays a vital role. Inline sensors and cameras continuously monitor chocolate viscosity, nougat density, caramel flow rate, peanut distribution, and packaging integrity. Manual samples are taken hourly and cut open for cross-sectional inspection. Taste tests are conducted daily by trained sensory teams who evaluate aroma, flavor, mouthfeel, and visual quality. Products that fail any stage of inspection are diverted, documented, and analyzed to prevent recurrence. Snickers factories are designed with food safety and hygiene as top priorities. Staff wear full PPE, including hairnets, gloves, and smocks. Entry to production areas requires hand washing, sanitization, and often passing through air showers or floor sanitizers. All surfaces are made of food-grade stainless steel, and machinery is built with clean-in-place systems that allow automated washing and sanitization between batches. Environmental sustainability is another integral part of Snickers manufacturing. Mars, the parent company, implements energy-efficient roasting systems that recover heat, water reclamation systems that treat and reuse rinse water, and LED lighting to cut emissions. Chocolate and nougat trimmings are collected and either reused in new batches or converted into animal feed, while packaging material waste is recycled or reused wherever possible. From the first roasted peanut to the moment the wrapper is sealed, the making of a Snickers bar involves over a dozen steps, hundreds of parameters, and thousands of quality checks. Every component, from the protein foam in the nougat to the precise shear profile of the caramel, the fat crystal structure of the chocolate, and the crunch of the peanuts, has been engineered and tested to deliver a consistent, craveable bite. This integration of traditional confectionery with high-efficiency industrial production is what enables Snickers to be produced in the millions each day, while maintaining the same rich, multi-layered flavor and texture that has made it a global staple for decades. The process begins with the careful selection and sourcing of raw ingredients. The primary components of KitKat bars include wheat flour, sugar, cocoa mass, cocoa butter, milk powder, vegetable oils, and emulsifiers. Nestlé, the brand behind KitKat, sources these ingredients from various regions worldwide, ensuring sustainability and adherence to strict quality standards. The cocoa used in KitKat is primarily sourced from the Nestlé Cocoa Plan, which promotes sustainable farming practices and fair trade. Once the raw materials arrive at the production facility, they undergo a series of inspections and tests to verify purity, consistency, and compliance with food safety regulations. This includes spectroscopic analysis for contaminants, moisture content testing, and sensory evaluations conducted by trained professionals. Once approved, the ingredients are stored in temperature-controlled silos and dispensing systems. The flour is kept in airtight storage to prevent contamination, while cocoa and milk powder are maintained under controlled humidity conditions to prevent clumping. Automated feeding systems transport these raw materials to the respective processing units, ensuring precise measurement and consistency in formulation. The first major step in KitKat production is wafer baking. The signature light and crispy wafer layers are created through a precise blending of wheat flour, water, sugar, and vegetable oils. Large industrial mixers, equipped with programmable logic controllers, ensure thorough mixing to produce a smooth and homogeneous batter. Once mixed, the batter is transferred via pressurized pumps to high-speed continuous wafer baking ovens. These ovens feature rotating baking plates that evenly distribute the batter across the surface, forming thin sheets of wafer. The baking plates operate at carefully controlled temperatures, typically around 180 to 200 degrees Celsius, ensuring uniform texture and color. The baked wafer sheets emerge golden brown and crisp, ready for the next stage. To enhance the crispness, the wafer sheets pass through a controlled cooling system. Conveyor belts transport the freshly baked wafers through a cooling tunnel, where calibrated fans gradually reduce the temperature to prevent thermal shock. The cooled wafers are then directed to the trimming and cutting station. Automated guillotine cutters trim the edges of the wafers to achieve uniform dimensions, ensuring consistency across all KitKat bars. Once trimmed, the wafers are transported to the layering station. Here, a fine layer of chocolate cream filling made from a precise blend of cocoa, sugar, and milk powder is evenly spread onto the wafers. Automated depositor machines ensure the filling is applied uniformly, maintaining the right thickness for optimal texture. The layering process continues with additional wafer sheets stacked on top, creating a multi-layered wafer slab. These slabs are then pressed under controlled pressure to bond the layers together without crushing the delicate structure. After layering, the wafer slabs proceed to the cutting stage. High-speed rotary or ultrasonic blade systems slice the large wafer sheets into precise rectangular portions, forming the individual KitKat fingers. Ultrasonic cutting technology is particularly effective in ensuring clean, precise cuts without generating excess crumbs or damaging the layers. The next crucial step is chocolate enrobing. The enrobing process begins with the preparation of molten milk chocolate, which is produced in large conching machines. These machines continuously grind and blend cocoa mass, cocoa butter, sugar, and milk powder, refining the mixture to achieve a smooth, velvety consistency. The conching process, which can last several hours, helps develop the rich, creamy texture and enhances the flavor profile of the chocolate. Once ready, the molten chocolate is fed into enrobing machines, where KitKat fingers pass through a curtain-like flow of chocolate. These enrobers ensure complete coverage, with excess chocolate removed using controlled air jets and vibrating conveyors. To achieve the signature glossy finish, the enrobed bars pass through a tempering unit, which carefully regulates the chocolate's crystallization process. This involves a precise cycle of heating, cooling, and reheating to stabilize the cocoa butter crystals, preventing bloom and ensuring a smooth, even texture. Following enrobing, the chocolate-covered KitKat bars enter a cooling tunnel. This tunnel, equipped with multi-zoned cooling technology, gradually reduces the temperature in stages to solidify the chocolate coating without causing cracks or condensation. The cooling process is carefully monitored using infrared sensors to maintain consistency. Once the chocolate is fully set, the KitKat bars move to the quality control and inspection stations. Advanced vision inspection systems, equipped with high-resolution cameras, scan each bar for defects, such as uneven coating, improper sizing, or misaligned layers. Bars that do not meet quality standards are automatically rejected by robotic sorting arms and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. After passing inspection, the KitKat bars are transported to high-speed wrapping machines. Individual bars are wrapped in foil or plastic film using heat sealing technology, ensuring airtight packaging that preserves freshness. These wrapped bars are then grouped into multi-packs, which are subsequently boxed using robotic case packers. The packaging design is carefully printed with product details, barcodes, and branding elements before final sealing. The packaged KitKat bars are then palletized for distribution. Automated palletizing systems stack the boxes onto pallets in a precise arrangement to optimize space utilization during transportation. These pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for delivery to distribution centers worldwide. The logistics process is carefully coordinated to ensure timely delivery, with real-time tracking systems monitoring shipments from factory to retailer. Throughout the entire production process, extensive quality control measures are in place to uphold product integrity. Each batch undergoes rigorous laboratory testing, including microbiological screening, allergen testing, and texture analysis. Data from all processing stages is logged in automated tracking systems, allowing full traceability and compliance with food safety regulations. While the fundamental principles of KitKat production remain consistent across different manufacturing plants, regional variations may exist to cater to local tastes and preferences. For example, KitKat flavors such as matcha green tea, strawberry, and sake are produced in Japan using specialized formulations. Some factories may also incorporate alternative chocolate blends, varying cocoa content to suit market demands. Nestlé continues to innovate and optimize KitKat production through advancements in automation, sustainability initiatives, and ingredient sourcing. Modern factories are increasingly utilizing AI-driven quality control systems, energy-efficient processing equipment, and eco-friendly packaging solutions to reduce environmental impact. With continuous improvements in manufacturing technology, KitKat remains a global favorite, offering consumers a consistently delightful chocolate experience in every bite. Mars bars, one of the most iconic chocolate confections in the world, are produced in highly sophisticated manufacturing facilities designed to ensure consistency, efficiency, and quality at every step of the process. The production of Mars bars involves multiple intricate stages, from sourcing and processing raw ingredients to forming, enrobing, cooling, and packaging the final product. Each step is meticulously controlled using advanced automation technology and stringent quality control measures to ensure the signature caramel, nougat, and chocolate combination is perfectly replicated in every bar. The process begins with the careful selection of raw ingredients. The main components of a Mars bar include sugar, cocoa mass, cocoa butter, skimmed milk powder, whey powder, palm fat, glucose syrup, lactose, milk fat, and egg whites. These ingredients are sourced from trusted suppliers and undergo rigorous quality assurance checks upon arrival at the factory. Sugar, which plays a crucial role in both the nougat and caramel layers, is stored in large silos, where it is kept dry and free from contamination. Cocoa products, including cocoa mass and cocoa butter are stored in climate-controlled environments to prevent degradation. Dairy ingredients such as skimmed milk powder and whey powder are tested for purity and consistency before use. Once the raw ingredients are approved, the first major stage in Mars bar production is the creation of the nougat layer. Nougat is a key structural component of the bar, providing a soft, chewy texture that contrasts with the caramel and chocolate. The nougat making process begins in large industrial mixing tanks, where a combination of sugar, glucose syrup, and water is heated to create a syrup. This syrup is then aerated using a whipping system, which incorporates fine air bubbles to achieve the desired light and fluffy texture. During this stage, egg whites or hydrolyzed soy protein are added as stabilizers to maintain the nougat's consistency. Once the nougat mixture reaches the proper texture, it is transferred onto a continuous conveyor belt, where it is spread into an even layer. This belt passes through a cooling tunnel to allow the nougat to set before it reaches the next stage of the process. The cooled nougat layer is then precisely cut into rectangular strips using high-speed guillotine cutters. These strips will form the base of each Mars bar. The next step in the process is the caramel layer. The caramel used in Mars bars is created through a controlled cooking process that involves heating sugar, glucose syrup, and milk ingredients to high temperatures. This process requires careful monitoring to achieve the perfect balance of sweetness and viscosity. Industrial batch cookers equipped with automated temperature controls ensure that the caramel reaches the ideal consistency before it is deposited onto the nougat base. The caramel is applied as a continuous sheet over the nougat layer, ensuring even distribution and uniform thickness. Once the caramel is applied, the combined nougat and caramel layers proceed through a controlled cooling tunnel, where the temperature is gradually reduced to allow the caramel to set without becoming too hard or sticky. This ensures that the layers remain cohesive and easy to cut in the next stage of production. After cooling, the layered nougat and caramel sheets are fed into an automated cutting system, which uses precision blades to slice them into individual bar-sized portions. These freshly cut bars are then transported via conveyor belts to the enrobing station, where they receive their final chocolate coating. The enrobing process is a critical step in Mars bar production, as it gives the bars their signature smooth milk chocolate exterior. The chocolate coating is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder, which is carefully tempered to achieve the perfect texture and glossy finish. The tempering process involves heating and cooling the chocolate in a controlled manner to ensure the cocoa butter crystals form a stable structure, preventing fat bloom and ensuring a smooth mouthfeel. At the enrobing station, the cut nougat and caramel bars pass through a curtain-like waterfall of molten chocolate, which fully coats them. Excess chocolate is removed using controlled air jets and vibrating conveyors to ensure an even layer without excessive buildup. Some factories use a two-stage enrobing process, where an initial thin layer of chocolate is applied as a base coat before the final, thicker chocolate layer is added. After enrobing, the chocolate-covered bars enter a multi-zone cooling tunnel, which gradually reduces their temperature in controlled stages. This cooling process allows the chocolate to set properly without developing cracks or a dull surface. The bars emerge from the cooling tunnel with a perfectly set chocolate shell, ready for the final stages of quality control and packaging. Quality control is a fundamental part of Mars bar production, ensuring that only bars meeting strict standards reach consumers. Automated vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, misshapen forms, or inconsistencies in size. Bars that do not meet the required specifications are automatically rejected and sent for reprocessing. Additional quality control measures include weight checks using precision weighing systems texture analysis, and sensory evaluations conducted by trained specialists. Once the bars pass quality inspection, they proceed to the packaging area, where high-speed wrapping machines individually wrap each bar in foil or plastic film. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and placed into branded cartons, which are sealed and labeled using automated case packing systems. The final step in the process is palletization and distribution. Automated palletizing systems stack the packaged bars onto pallets in a precise arrangement to optimize space utilization during transportation. The pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retail stores and supermarkets worldwide. The entire logistics process is carefully coordinated to ensure timely delivery while maintaining the product's freshness and quality. Throughout the entire manufacturing process, Mars maintains stringent quality control and food safety standards. Each production batch undergoes extensive laboratory testing, including microbial analysis, allergen testing, and moisture content verification. The company also invests in sustainable sourcing initiatives, ensuring that key ingredients such as cocoa and palm oil are responsibly sourced to minimize environmental impact. Different Mars manufacturing facilities may incorporate slight variations in processing techniques based on regional ingredient availability, consumer preferences, or proprietary formulations. Some facilities may use alternative chocolate blends with varying cocoa content to cater to specific markets, while others may modify the nougat formulation for textural differences. Additionally, Mars continuously invests in research and development to improve efficiency, reduce energy consumption, and enhance sustainability in its production processes. With advancements in automation, AI-driven quality control systems, and eco-friendly packaging innovations, the production of Mars bars continues to evolve while maintaining the signature taste and texture that consumers have loved for generations. Twix, one of the world's most beloved chocolate bars, is manufactured using a highly sophisticated and automated process that ensures each bar maintains its signature combination of crunchy biscuit, smooth caramel, and creamy milk chocolate coating. The production of Twix bars occurs in state-of-the-art factories that utilize precision engineering, cutting-edge food processing technology, and rigorous quality control protocols. From the sourcing of raw ingredients to packaging and distribution, every step is carefully orchestrated to guarantee consistency, efficiency, and superior taste. The process begins with the selection and procurement of high-quality raw materials. The key ingredients in Twix bars include wheat flour, sugar, palm oil, cocoa butter, skimmed milk powder, cocoa mass, lactose, whey powder, salt, and emulsifiers. These ingredients are sourced from carefully vetted suppliers who must meet strict food safety and sustainability requirements. For instance, the cocoa used in Twix bars is sourced through Mars' Cocoa for Generations initiative, ensuring ethical sourcing and environmental responsibility. Similarly, the palm oil used in the biscuits and caramel is certified sustainable to reduce environmental impact. Upon arrival at the manufacturing facility, the raw ingredients undergo thorough quality checks before entering the production process. These checks include spectroscopic analysis to detect contaminants, moisture content analysis to ensure freshness, and sensory evaluations to verify taste and aroma. Ingredients that meet the necessary standards are then stored in temperature-controlled silos and storage units to maintain their quality. The first step in the actual production process is the creation of the biscuit base. Twix bars are distinguished by their crunchy, shortbread-like biscuit layer, which requires precise preparation and baking. The process begins in large industrial mixers, where wheat flour, sugar, palm oil, and leavening agents are combined to form a dough. The mixing process is carefully timed to ensure the dough reaches the ideal consistency, firm enough to hold its shape during baking, yet tender enough to create the signature crisp texture. Once the dough is fully mixed, it is transferred to an automated sheeting system. This system rolls the dough into a uniform sheet of the exact thickness required for Twix bars. The sheeted dough then moves to a rotary cutting machine, which stamps out individual biscuit fingers. Each biscuit is precisely cut to ensure uniform size and shape, allowing for seamless assembly in later stages. The cut dough pieces are placed onto conveyor belts and transported into a large industrial baking oven. These ovens operate using a continuous baking system where the biscuit fingers travel through different heat zones that gradually bake them to perfection. The baking temperature is carefully controlled, typically ranging between 180 to 200 degrees Celsius, 356 to 392 degrees Fahrenheit, ensuring that each biscuit is evenly baked to a golden brown. Advanced infrared sensors monitor the biscuits throughout the baking process, ensuring uniformity in color, texture, and moisture content. Once fully baked, the biscuits pass through a cooling tunnel that gradually reduces their temperature, preventing cracking or breakage. Next, the caramel layer is prepared. The caramel used in Twix bars is made from a precise blend of sugar, glucose syrup, milk, and butter. This mixture is heated in large stainless steel batch cookers, where it undergoes controlled caramelization. The temperature and cooking time are crucial in achieving the perfect consistency, thick enough to stay in place on the biscuit, but soft enough to deliver a smooth, chewy texture. Once the caramel reaches the desired consistency, it is transferred to a continuous depositor system. This machine evenly dispenses a uniform layer of caramel onto each biscuit. The caramel application must be carefully controlled to ensure consistency in thickness across all bars. Any inconsistencies could lead to difficulties in chocolate enrobing or affect the final texture. With the caramel applied, the bars move along the conveyor belt to a cooling station, where they pass through a controlled cooling tunnel. This tunnel gradually reduces the temperature of the caramel, allowing it to set properly while maintaining its soft, chewy texture. After cooling, the caramel-coated biscuits are ready for the enrobing process, where they will be covered in rich milk chocolate. The enrobing process is one of the most critical steps in Twix production. The milk chocolate coating is prepared in large conching machines, which continuously grind and refine cocoa mass, cocoa butter, sugar, and milk powder. This process enhances the texture and flavor of the chocolate, ensuring a smooth, creamy consistency. The chocolate is then tempered, a controlled heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering is essential to achieving the signature glossy finish and preventing fat bloom, white streaks that can appear on improperly tempered chocolate. At the enrobing station, the caramel-topped biscuits pass through a continuous chocolate waterfall. This ensures that each bar is fully coated in an even layer of chocolate. Any excess chocolate is removed using controlled air jets and vibrating conveyors, which help distribute the chocolate evenly without excessive buildup. Some factories employ a two-stage enrobing process, where a thin base coat of chocolate is applied first to ensure better adhesion before the final, thicker chocolate layer is added. Once the bars are coated, they enter a multi-zone cooling tunnel. This tunnel is divided into different temperature zones that gradually reduce the temperature, allowing the chocolate to set perfectly without cracking or becoming dull. The bars emerge from the cooling tunnel with a firm, glossy chocolate coating, ready for the next stage of production. Quality control is a top priority at every stage of Twix production. After cooling, the bars pass through a series of automated inspection systems. High-speed vision cameras scan each bar for inconsistencies in chocolate coating, caramel distribution, and overall shape. Any bars that do not meet specifications are automatically rejected and sent for reprocessing. In addition to visual inspections, quality control teams conduct random weight checks, moisture analysis, and sensory evaluations to ensure that each batch meets Mars's stringent quality standards. Once the bars have passed inspection, they move to the packaging stage. Twix bars are individually wrapped using high-speed horizontal flow wrapping machines. These machines use heat-sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs, which are sealed in branded cartons using automated case packing systems. After packaging, the final step in the process is palletization and distribution. Robotic palletizing systems stack the packaged bars onto pallets in precise arrangements, optimizing space for transport. The pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Mars utilizes an advanced logistics network to ensure efficient delivery while maintaining product freshness. Throughout the entire production process, Mars adheres to strict food safety and sustainability standards. Each batch undergoes rigorous laboratory testing, including microbiological analysis, allergen testing, and texture verification. The company also invests in eco-friendly initiatives, such as reducing energy consumption in manufacturing and using recyclable packaging materials. Different Mars factories may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate formulations with varying cocoa content, while others may adjust the caramel consistency based on market preferences. Additionally, limited edition Twix flavors, such as Twix white chocolate and Twix peanut butter, require modifications in ingredient formulation and processing techniques. As consumer demand for innovative flavors and healthier options grows, Mars continues to invest in research and development to improve Twix production. Recent advancements in AI-driven quality control, robotic automation, and sustainable ingredient sourcing are shaping the future of Twix manufacturing. Despite these innovations, the core principles of precision, consistency, and quality remain unchanged, ensuring that every Twix bar delivers the signature, crunchy, chewy, and chocolatey experience that consumers love. The making of a Hershey's chocolate bar is a complex, highly automated process that combines tradition with cutting-edge technology. From sourcing high-quality cocoa beans to wrapping the final product, every step is optimized for efficiency, consistency, and taste. The journey of a Hershey's bar begins with the careful selection of raw ingredients sourced from around the world. Cocoa, sugar, milk, and other ingredients are carefully tested to ensure they meet the company's high standards before they are transformed into the iconic chocolate bars that have been loved for generations. At the heart of every Hershey's chocolate bar is cocoa. The company sources its cocoa beans primarily from Ghana, Côte d'Ivoire, and Ecuador, regions known for producing high-quality beans with robust flavor profiles. Cocoa farmers in these areas harvest the ripe pods, extract the cocoa beans, and allow them to ferment for several days to develop their characteristic chocolatey taste. Once dried, the beans are shipped to Hershey's production facilities, where they undergo rigorous quality checks. Each shipment is tested for moisture content, flavor consistency, and the absence of contaminants. Only the highest quality beans make it through this stringent selection process. Once approved, the cocoa beans are sent to the roasting stage. Large industrial roasters expose the beans to carefully controlled heat, typically between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit, depending on the desired flavor profile. The roasting process is essential for developing the deep, complex flavors of chocolate. Different roasting profiles are used depending on whether the beans will be used for milk chocolate, dark chocolate, or other specialty products. After roasting, the cocoa beans enter the winnowing process. Specialized machinery cracks the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both the cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, dark paste known as chocolate liquor, which contains no alcohol despite its name. This chocolate liquor is the base for all Hershey's chocolate products. For Hershey's classic milk chocolate bars, chocolate liquor is combined with sugar, milk, and cocoa butter. The milk used in Hershey's chocolate is a key ingredient that gives it its distinctive taste. Unlike many European chocolates that use powdered or condensed milk, Hershey's uses fresh milk sourced from dairy farms in Pennsylvania and surrounding states. The milk is pasteurized and condensed before being blended with sugar to create a sweet, creamy base. The next stage in the process is refining. The chocolate mixture is run through a series of steel rollers that grind the particles to an ultra-fine consistency. This refining process is crucial for creating a smooth, melt-in-your-mouth texture. The finer the particles, the smoother the final chocolate will be. Once refined, the chocolate undergoes conching, a critical process that enhances flavor and texture. Conching machines, which resemble large industrial mixers, continuously stir the chocolate at controlled temperatures for several hours. This process aerates the chocolate, allowing unwanted acidic compounds to evaporate while enhancing its creamy mouthfeel. Hershey's uses a proprietary conching method that contributes to its signature flavor, which has a slightly tangy undertone due to controlled acidity in the milk. After conching, the chocolate moves to the tempering stage. Tempering is the process of heating and cooling chocolate in a precise manner to stabilize the cocoa butter crystals. Proper tempering ensures that Hershey's bars have a glossy finish, a firm snap, and a long shelf life. If the chocolate were not tempered correctly, it could develop fat bloom, a whitish streaking effect caused by unstable cocoa butter. Now, the tempered chocolate is ready for molding. Automated machines pour precise amounts of liquid chocolate into bar-shaped molds, which are then vibrated to remove air bubbles and ensure even distribution. The molds travel along a conveyor system into a cooling tunnel, where the chocolate solidifies into its final shape. Once cooled, the bars are ejected from their molds and transported via conveyor belts to the packaging area. Here, high-speed wrapping machines encase each bar in foil and branded paper sleeves, protecting the chocolate from moisture and light while ensuring a fresh, appealing presentation. Throughout the entire process, strict quality control measures are in place. High-resolution vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or size inconsistencies. Bars that do not meet specifications are automatically rejected and sent for reprocessing. Additionally, random sensory evaluations are conducted by trained taste testers to ensure that the flavor, texture, and overall quality remain consistent. Once packaged, the final step is palletization and distribution. Automated robotic arms stack the packaged bars onto pallets, which are then shrink-wrapped for stability. These pallets are loaded onto temperature-controlled trucks and shipped to retailers worldwide. Hershey's operates an advanced logistics network that ensures timely delivery while maintaining product freshness. The entire manufacturing process is designed for efficiency, consistency, and sustainability. Hershey's continues to invest in eco-friendly initiatives, such as reducing water and energy consumption in production, using ethically sourced cocoa, and optimizing packaging materials to minimize waste. Different Hershey's factories may employ slight variations in processing techniques based on regional preferences and ingredient availability. Additionally, specialty products like Hershey's cookies and cream bars or Hershey's dark chocolate require modifications in ingredient formulation and processing times. As the chocolate industry continues to evolve, Hershey's remains at the forefront of innovation, combining tradition with advanced manufacturing techniques to produce its iconic chocolate bars. Through precision engineering, strict quality control, and a commitment to excellence, Hershey's ensures that every bar delivers the same beloved taste that generations have enjoyed. The making of Toblerone, the iconic triangular chocolate bar, is a masterclass in precision engineering, premium ingredient selection, and automated manufacturing processes. Unlike conventional chocolate bars, Toblerone stands out for its distinctive shape, rich Swiss milk chocolate, and the inclusion of honey and almond nougat. Every step, from sourcing the finest ingredients to molding the signature peaks, is meticulously controlled to ensure quality, consistency, and adherence to the Swiss chocolate making tradition. The process begins with sourcing high-quality ingredients. Toblerone's signature flavor comes from its carefully selected components: Swiss milk, sugar, cocoa mass, cocoa butter, honey, almonds, and egg whites. The milk, sourced from Swiss dairy farms, is a critical ingredient that contributes to the creamy texture. The cocoa is sourced from sustainable farms in Ghana and Ecuador, where beans are hand-harvested, fermented, and dried under strict quality control measures. Almonds are procured from select suppliers, ensuring they meet the required standards of size, flavor, and crunch. The honey, a key component that adds a subtle sweetness, is sourced from European beekeepers specializing in high-quality aromatic varieties. Once the ingredients arrive at the production facility, they undergo rigorous quality checks. Advanced spectroscopic analysis, moisture content testing, and flavor profiling ensure that each ingredient meets the brand's high standards. The cocoa beans are then roasted at carefully controlled temperatures to develop their deep, complex flavor. Different roasting profiles are used depending on whether the beans will be used for Toblerone's milk, dark, or white chocolate variations. After roasting, the cocoa beans move to the winnowing stage, where high-powered machinery cracks them open and removes the husks. The remaining cocoa nibs, which contain the essence of the chocolate, are then finely ground into a thick, rich paste known as chocolate liquor. This forms the base of Toblerone's chocolate. The chocolate liquor is blended with sugar, cocoa butter, and Swiss milk powder to create the signature, smooth and creamy chocolate mixture. The next step in the process is refining. The chocolate mixture passes through a series of heavy-duty steel rollers that break down the particles to an ultra-fine consistency. This is crucial in achieving the signature melt-in-your-mouth texture. The refining process also helps blend the ingredients evenly, ensuring a perfectly smooth mixture. Following refining, the chocolate undergoes conching, a process that enhances its texture and flavor. Large conching machines continuously mix, aerate, and heat the chocolate for several hours, allowing volatile acids to evaporate and the flavors to develop fully. Toblerone's conching process is fine-tuned to create a silky texture and a well-rounded, rich taste. Meanwhile, the honey and almond nougat mixture is prepared in a separate area of the factory. Sugar, honey, and egg whites are heated and aerated to create a light, chewy nougat. Almonds, which have been roasted to bring out their nutty aroma, are chopped into small pieces and folded into the nougat mixture. The nougat is then cooled and ground into fine pieces before being incorporated into the chocolate. Once the chocolate has completed the conching process, the finely ground nougat mixture is carefully folded into it, ensuring even distribution. This step is crucial in maintaining the signature texture and taste of Toblerone. With the chocolate and nougat mixture fully blended, the next stage is tempering. Tempering is a precise process of heating and cooling chocolate in a controlled manner to stabilize the cocoa butter crystals. Proper tempering ensures that the chocolate has a glossy finish, a firm snap, and a smooth texture. Toblerone's tempering process is carefully calibrated to achieve the ideal consistency before molding. Molding is where Toblerone's iconic shape comes to life. The tempered chocolate is poured into custom-designed triangular molds that give the bar its distinctive peaks. The molds are gently vibrated to remove air bubbles and ensure even distribution of the chocolate. After molding, the bars pass through a cooling tunnel where they are gradually cooled to allow the chocolate to set perfectly without cracks or imperfections. Once solidified, the bars are removed from the molds and transported to the quality control station. Each bar is inspected using high-resolution vision cameras, which detect any inconsistencies in shape, texture, or coating. Automated sorting systems remove any defective bars, ensuring that only perfectly shaped Toblerone bars proceed to packaging. The packaging process is designed to maintain the freshness and integrity of the chocolate. Toblerone bars are individually wrapped in foil to protect them from moisture and light, then placed into the iconic triangular cardboard cartons. High-speed packaging machines fold and seal the cartons with precision, ensuring that the bars remain securely enclosed. Following packaging, the bars are palletized using robotic systems, stacked carefully for stability during transport. These pallets are shrink-wrapped and loaded onto trucks for distribution to markets around the world. Temperature-controlled logistics ensure that the chocolate remains in perfect condition during transit. Throughout the entire manufacturing process, Toblerone maintains strict quality control measures. Each batch undergoes laboratory testing, including texture analysis, microbial screening, and taste assessments conducted by trained specialists. Data is continuously logged in automated tracking systems, allowing for full traceability of every Toblerone bar produced. Different Toblerone manufacturing facilities may employ slight variations in processing techniques depending on regional ingredient availability and market preferences. Specialty additions, such as Toblerone white chocolate or Toblerone dark, require slight modifications in ingredient formulations and processing steps. As consumer preferences evolve, Toblerone continues to innovate while maintaining the brand's heritage of Swiss chocolate craftsmanship. Investments in sustainable cocoa sourcing, eco-friendly packaging solutions, and advanced automation ensure that Toblerone remains a global favorite while reducing its environmental footprint. Through precision engineering, time-honored techniques, and a commitment to quality, every Toblerone bar delivers the signature taste and texture that chocolate lovers around the world cherish. The production of Snickers, one of the world's most popular chocolate bars, is a highly automated and meticulously controlled process designed for efficiency, consistency, and large-scale output. With its signature combination of nougat, caramel, peanuts, and milk chocolate, Snickers is produced in state-of-the-art facilities that use cutting-edge food processing technology, ensuring that every bar meets the brand's high-quality standards. From sourcing the finest raw ingredients to packaging and distribution, every step is optimized to deliver the same taste, texture, and satisfaction in every bite. The journey of a Snickers bar begins with the careful selection of raw materials. The main components include sugar, peanuts, milk powder, cocoa mass, cocoa butter, palm oil, glucose syrup, egg whites, and emulsifiers. These ingredients are sourced from carefully vetted suppliers, ensuring compliance with strict food safety and sustainability standards. Mars, the company behind Snickers, prioritizes responsible ingredient sourcing, ensuring that cocoa is ethically obtained through its Cocoa for Generations program, which promotes fair labor practices and sustainable farming methods. Peanuts, another crucial ingredient, are primarily sourced from the United States, where they are grown under controlled conditions to maintain size, flavor, and crunch. Once the ingredients arrive at the manufacturing facility, they undergo a rigorous quality control process. Each batch is tested for moisture content, purity, and potential contaminants. Peanuts, in particular, go through an additional inspection phase. where they are sorted by size and quality. High-speed optical sorting machines remove any defective or discolored peanuts, ensuring that only the best nuts make it into Snickers bars. The first major step in the Snickers production process is creating the nougat base. Nougat provides the chewy texture that forms the foundation of the bar. It is made by combining sugar, corn syrup, and water, which are heated in large industrial cooking vats to create a syrup. This syrup is then aerated using high-powered whipping machines, which incorporate fine air bubbles, giving the nougat its characteristic light and chewy texture. Egg whites or soy protein are added as stabilizers to help maintain consistency. Once aerated, the nougat is spread onto a moving conveyor belt in a continuous sheet, where it is allowed to cool and set. This process is carefully controlled to prevent the nougat from becoming too hard or too soft. Automated guillotine cutters then slice the nougat sheet into uniform rectangular portions, ensuring that each piece is the exact size required for Snickers bars. Next comes the caramel layer. The caramel in Snickers is made from a blend of sugar, glucose syrup, milk, and butter, which is heated in large stainless steel batch cookers. The temperature is carefully monitored to achieve the perfect viscosity, thick enough to hold its shape, but soft enough to provide a smooth, chewy texture. Once cooked to perfection, the caramel is poured in a controlled stream onto the nougat base. The caramel-covered nougat passes through a cooling tunnel, where it sets just enough to be firm, but still pliable. Now it's time to add the peanuts. Before being incorporated into the bars, the peanuts are roasted in industrial ovens to enhance their flavor and crunch. After roasting, they are cooled and evenly distributed over the caramel layer using precision peanut dispensers. These machines ensure that each bar receives the right amount of peanuts, maintaining uniformity across all Snickers bars. Once the peanuts are in place, the layered nougat, caramel, and peanut sheet moves to the cutting stage. High-speed rotary blades slice the continuous sheet into individual bar-sized portions. Each cut must be precise, ensuring that the caramel and nougat layers remain intact while maintaining a consistent size. The next critical step is chocolate enrobing. The milk chocolate coating used for Snickers bars is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder. This mixture is refined and conched in large machines that continuously grind the chocolate to achieve a smooth texture. The chocolate is then tempered, a process that involves controlled heating and cooling to stabilize the cocoa butter crystals. Proper tempering ensures a glossy finish and prevents fat bloom, which can cause chocolate to develop a dull appearance. At the enrobing station, the cut bars pass through a waterfall of liquid milk chocolate, fully coating them. Excess chocolate is removed using controlled air jets and vibrating conveyors, ensuring an even layer without excessive buildup. Some factories use a two-stage enrobing process, where a thin base coat of chocolate is applied first to create a stable foundation before the final. Thicker chocolate layer is added. After enrobing, the bars enter a multi-zone cooling tunnel. This tunnel gradually lowers the temperature in controlled stages, allowing the chocolate to set properly without developing cracks or dull spots. Once fully cooled, the Snickers bars emerge with a perfectly solidified chocolate coating, ready for quality inspection. Quality control is a critical component of Snickers production. Each bar undergoes a series of automated inspections to ensure that it meets strict specifications. High-speed vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, improper size, or misshapen layers. Any bars that do not meet the required standards are automatically rejected and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. Once the bars have passed inspection, they move to the packaging stage. Snickers bars are individually wrapped in plastic film using high-speed horizontal flow wrapping machines. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and packed into branded cartons using automated case packers. The final step in the process is palletization and distribution. Automated systems stack the packaged cartons onto pallets in precise formations, optimizing space for transport. These pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Snickers bars are shipped to over 70 countries, requiring an advanced logistics network to ensure that they arrive fresh and in perfect condition. Throughout the entire production process, Mars maintains stringent food safety and sustainability practices. Each batch undergoes extensive laboratory testing, including microbiological screening, allergen testing, and texture verification. The company also invests in sustainable ingredient sourcing, reducing its environmental footprint through energy-efficient manufacturing processes and eco-friendly packaging solutions. Different Snickers manufacturing facilities may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate blends with varying cocoa content, while others may modify the nougat or caramel consistency based on market demands. Additionally, special edition Snickers bars, such as Snickers almond or Snickers peanut butter, require modifications in ingredient formulation and production methods. As consumer preferences evolve, Mars continues to innovate while maintaining the classic Snickers taste and texture. Advancements in automation, AI-driven quality control, and sustainable manufacturing practices are shaping the future of Snickers production. Despite these innovations, the fundamental principles of precision, consistency, and quality remain unchanged, ensuring that every Snickers bar delivers the same delicious combination of chewy nougat, gooey caramel, crunchy peanuts, and smooth milk chocolate that has made it a favorite among chocolate lovers worldwide. The production of Tony's Chocolonely chocolate bars is a carefully designed process that emphasizes ethical sourcing, sustainability, and high-quality chocolate-making techniques. Unlike traditional chocolate brands, Tony's Chocolonely is dedicated to creating a slave-free chocolate industry, ensuring that every step in the supply chain is transparent and fair. From sourcing cocoa beans from cooperatives in West Africa to molding and packaging the final bars, the production process is a seamless blend of traditional craftsmanship and modern automation. The journey of a Tony's Chocolonely bar begins with cocoa sourcing. The company partners with cooperatives in Ghana and Côte d'Ivoire, regions that are known for cocoa production, but also face significant challenges related to child labor and unfair wages. Tony's Chocolonely implements direct trade practices, paying a premium for cocoa and providing additional support to farmers through training programs and financial resources. This ensures that the beans are ethically sourced while maintaining a high standard of quality. Once harvested, the cocoa beans go through a meticulous post-harvest process. Farmers ferment the beans for several days, a crucial step that develops the deep, complex flavors needed for premium chocolate. After fermentation, the beans are spread out under the sun to dry, reducing moisture content and preventing mold growth. When dried to the appropriate level, the beans are packed into jute sacks and shipped to Tony's Chocolonely's processing facilities. Upon arrival at the factory, the beans undergo rigorous quality control checks. Samples from each shipment are tested for moisture levels, flavor consistency, and potential contaminants. Beans that pass inspection are stored in climate-controlled silos to maintain freshness before entering the production line. The first step in the chocolate making process is roasting. Large industrial roasting machines heat the beans at precise temperatures, usually between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit. This process enhances the natural chocolate flavors and eliminates unwanted bitterness. The roasting time and temperature depend on the type of chocolate being produced. Dark chocolate requires a slightly longer roasting process than milk chocolate to develop its rich, bold flavors. Once roasted, the beans enter the winnowing process. A specialized machine cracks open the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both cocoa solids and cocoa butter, the essential components of chocolate. The nibs are then ground into a thick, smooth paste known as chocolate liquor. This process, carried out by industrial grinders, reduces the particle size of the nibs, creating a velvety consistency. At this stage, different chocolate variations begin to take shape. For Tony's Chocolonely's milk chocolate bars, the chocolate liquor is combined with sugar, milk powder, and additional cocoa butter to create a creamy texture. For dark chocolate, higher cocoa percentages are used with less sugar and no milk. The next step in the process is refining. The chocolate mixture is passed through heavy-duty steel rollers that grind the ingredients into ultra-fine particles. This step is crucial for achieving the smooth texture that defines high-quality chocolate. The finer the particles, the better the melt-in-your-mouth experience. Following refining, the chocolate undergoes conching, a process that enhances both texture and flavor. Large conching machines continuously mix and aerate the chocolate for several hours, allowing any residual acidity to evaporate while intensifying the chocolate's richness. The conching time varies depending on the desired flavor profile. Longer conching results in a smoother, more developed taste. After conching, the chocolate is tempered, a precise heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering ensures that Tony's Chocolonely bars have a glossy finish, a satisfying snap when broken, and a long shelf life without developing fat bloom, the white streaks that can appear on improperly tempered chocolate. Once tempered, the liquid chocolate is ready for molding. Unlike most chocolate bars, Tony's Chocolonely bars are intentionally molded in an uneven pattern, symbolizing the unequal distribution of wealth in the chocolate industry. Automated machines pour precise amounts of chocolate into these custom-designed molds, which are then gently vibrated to remove air bubbles and ensure even distribution. The molds are then transferred to a cooling tunnel, where the chocolate gradually solidifies under controlled temperatures. This process prevents the bars from developing surface defects and ensures that they retain their perfect shape. Once the chocolate has fully set, the bars are ejected from the molds and sent to the quality control station. High-speed vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or uneven texture. Any bars that do not meet the required standards are removed from the production line and either reprocessed or discarded. After passing quality checks, the bars move to the packaging stage. Tony's Chocolonely uses brightly colored, easily recognizable wrappers, each featuring bold typography and branding. The packaging process is fully automated, with high-speed wrapping machines, sealing each bar in foil and paper to protect it from moisture and contamination. The wrapped bars are then packed into cartons using robotic case packers. The final step in the process is palletization and distribution. Automated robotic systems stack the packaged bars onto pallets in a precise arrangement, optimizing space for transport. It all begins with the careful sourcing and intake of raw chicken, a process that is both biologically sensitive and highly mechanized to maintain consistent quality and food safety. The chickens destined for KFC facilities are selected from specific poultry farms that follow stringent guidelines set by both KFC's corporate standards and local regulatory bodies. These farms raise broiler chickens, a breed specifically developed for rapid growth and high meat yield, particularly in the breast, and thigh areas. To ensure consistency in texture and flavor, the birds are typically grown under controlled feeding regimens with strict monitoring of their diet, environment, and health status from hatchery to harvest. Once the birds reach the appropriate weight and age, usually between 5 to 7 weeks, they are transported live in temperature-regulated, well-ventilated trucks to the processing facility. Upon arrival, the birds are unloaded through an automated conveyor system and transferred to a staging area that uses dim lighting and gentle sound cues to keep the animals calm. This pre-processing environment is crucial for maintaining meat quality, as high stress can cause conditions like pale, soft, and exudative meat, or dark, firm, dry meat, which are both unsuitable for KFC's strict quality requirements. The first critical step in the factory is stunning, which is done using controlled atmosphere stunning, a method that introduces carbon dioxide in gradually increasing concentrations to render the chickens unconscious. This technique is widely considered more humane and helps preserve the quality of the meat. Once the birds are unconscious, they move to the next stage, where an automated system makes a precise incision to the neck, ensuring rapid and thorough bleeding. The bleeding process is closely timed and monitored using sensors and timers to maximize the efficiency of blood removal, which is essential not only for meat appearance and shelf life, but also for meeting food safety regulations. Following exsanguination, the birds proceed through a high-capacity scalding tank filled with water heated to approximately 60 degrees Celsius. This stage loosens the feathers by relaxing the collagen in the feather follicles. The duration and temperature are controlled to a fine margin to ensure that the skin is neither overcooked nor damaged. After scalding, the birds are transferred into rotary feather pluckers, drum-shaped machines lined with soft rubber fingers that rotate at high speeds. These fingers remove feathers through a gentle abrasive action. Any residual feathers, particularly around the wings and tail, are removed by additional targeted plucking devices or hand finishing stations, depending on the processing line speed and factory setup. The next step is evisceration, a highly mechanized process involving robotic arms and vision-guided machinery. The system first makes a precise incision along the abdominal cavity before extracting the internal organs. This includes the heart, liver, gizzard, and intestines, which are separated into byproduct streams for different uses or disposal. Each carcass is inspected by high-speed cameras equipped with AI-powered image recognition software to detect any abnormalities such as bruising, discoloration, or contamination. Chickens that fail this inspection are automatically diverted from the production line for further examination or removal. This real-time quality assurance technology helps maintain a consistent and safe supply of chicken for further processing. Now it's time to move on to the chilling process, which is absolutely vital for halting bacterial growth and ensuring a clean transition from slaughter to further cutting and seasoning. KFC factories typically use an immersion chilling method, where eviscerated chickens are conveyed through long stainless steel tanks filled with chlorinated cold water, maintained at around 0 to 4 degrees Celsius. The flow of water is designed in a countercurrent pattern, meaning the cleanest water contacts the most recently added chickens, ensuring optimal hygiene. This step rapidly reduces the internal temperature of the chicken from roughly 40 degrees Celsius to below 4 degrees within an hour, thereby locking in freshness and significantly extending the shelf life of the meat. After chilling, the carcasses proceed to the cutting and portioning stage. This part of the process is perhaps one of the most intricate in the factory. Specialized rotary cutting machines equipped with lasers and 3D scanners assess the size and density of each chicken in real time. Based on this data, programmable robotic blades segment the carcasses into uniform cuts: legs, thighs, wings, breasts, and keels. Each piece is sized to match strict dimensional and weight criteria, which are crucial for ensuring consistent cooking times and presentation across all KFC restaurants worldwide. The system is calibrated to yield the optimal number of each type of piece from every bird, reducing waste and maximizing efficiency. If a cut doesn't meet the precise size range, it is automatically redirected for use in alternative products like tenders or popcorn chicken. The next phase focuses on marination, a process that introduces moisture, flavor, and functional ingredients into the chicken to enhance both taste and texture. Once portioned, the chicken pieces are loaded into massive stainless steel tumblers, each capable of holding hundreds of kilograms of product. Inside the tumbler, a proprietary liquid marinade blend is introduced. While the exact formulation is a closely guarded secret, the marinade typically includes salt, phosphate-based tenderizers, flavoring agents, and sometimes buttermilk solids to create the tender, juicy interior that KFC is known for. The tumbling action lasts anywhere from 15 to 30 minutes, depending on the batch size and desired intensity. And the drum rotates on multiple axes to ensure that every surface of every piece of chicken is exposed to the marinade. This mechanical agitation also helps the meat fibers absorb the liquid more thoroughly, contributing to the product's juiciness even after high temperature frying. But up next comes the breading stage, which is arguably the most iconic part of KFC's production process. After marination, the chicken is gently drained and transferred to the breading stations, where each piece is coated in the proprietary blend of flour and seasoning known famously as the 11 herbs and spices. To replicate the hand-breaded quality that KFC is known for, even at industrial scale, specialized breading drums are used. These drums simulate the hand-tossing action by gently rolling the chicken pieces in the seasoned flour, while pneumatic paddles and vibration systems ensure that every crevice is fully coated. At this point, moisture content is carefully controlled to ensure adhesion without creating clumps or overly moist surfaces, which would ruin the crispy texture during frying. Once breaded, the chicken moves immediately to the par frying or pre-frying stage. This step is critical for setting the breading so it doesn't fall off during full cooking at the restaurant. The breaded pieces are passed through continuous fryers filled with hot oil maintained at temperatures between 170 to 180 degrees Celsius. In this stage, the chicken is fried for a short duration, usually 90 to 120 seconds, just enough to solidify the coating and begin the Maillard reaction, which is responsible for the development of flavor and the golden color. The oil used in this step is filtered and refreshed continuously using an inline oil management system that maintains optimal frying conditions and ensures that the final product is never tainted by burnt residues or off flavors. The partially cooked chicken is then lifted out of the fryer via a conveyor system and deposited onto a draining belt that uses both gravity and air jets to remove excess oil. Now, it's time to transition to the flash freezing process. This is where partially cooked chicken is rapidly frozen to lock in all the flavors, textures, and moisture absorbed during marination and breading. Each piece is conveyed into a spiral freezer or impingement freezer, both of which use sub-zero air blasts or liquid nitrogen vapor to drop the temperature of the chicken from over 60 degrees Celsius to below minus 18 degrees in under 10 minutes. Rapid freezing is crucial to prevent the formation of large ice crystals, which can damage the cellular structure of the meat and result in dryness or texture loss after final cooking. During this process, each piece is also individually quick frozen, which prevents clumping and allows for precise portioning when packaging. The next step in the factory process is the automated packaging of the individually quick frozen, par-fried chicken pieces, a phase that combines high-speed precision machinery with meticulous control over product integrity. Once the chicken emerges from the spiral or impingement freezer, each piece is conveyed to a sophisticated vision inspection system that performs a final quality assurance check. High-resolution cameras and laser scanners examine each piece for uniform breading coverage, appropriate size, and the absence of any structural defects like broken bones or irregular shapes. Pieces that fail this inspection are removed from the line using targeted air jets and routed for rework or disposal, depending on factory protocol. Once the pieces pass inspection, they are conveyed into a portioning station where intelligent weighing and sorting systems group them into standardized sets that align with KFC's iconic bucket meal configurations. These could be 8-piece, 12-piece, or 16-piece configurations, depending on the regional product lineup. Multi-head weighing machines calculate the total weight and count of each portion, ensuring that every pack not only meets visual and compositional standards, but also falls within a narrowly defined weight range for inventory accuracy and consistent customer experience. These grouping systems operate at incredibly high speeds, hundreds of portions per minute, with tolerances as tight as +1 gram. Each portion of chicken pieces is then dropped into a form-fill-seal machine or into pre-formed plastic pouches, depending on the final packaging format. The form-fill-seal machines shape a plastic film into a bag, load it with chicken, flush it with a nitrogen-rich gas to minimize oxygen, and heat seal it in a continuous, uninterrupted process. Modified atmosphere packaging is used here to extend shelf life while preventing freezer burn or flavor degradation. The gas blend, often a mix of nitrogen and carbon dioxide, inhibits microbial growth and oxidation without adding any chemicals or preservatives. After sealing, the packages are labeled with all necessary tracking and compliance information. High-speed thermal transfer printers apply labels that contain lot numbers, plant codes, production timestamps, and freeze dates. These labels also include data matrix barcodes or QR codes used for traceability, allowing KFC's central quality control teams to trace every package back to its exact farm, batch, and processing line in the event of a recall or audit. Automated verification systems scan each label for accuracy and readability. Any incorrectly labeled packages are automatically rejected from the line and placed in a designated review bin for manual inspection. Now it's time to move on to case packing, where multiple individually sealed packs of chicken are grouped into corrugated cardboard boxes, each built to withstand long-distance cold chain transportation. Robotic arms equipped with vacuum suction grippers pick and place the sealed bags into the boxes with extreme precision, ensuring that space is maximized while maintaining the integrity of the chicken. Each case typically holds a specific number of meals or bucket configurations and is marked with a unique identifier. Once filled, the boxes are sealed using automated taping machines and pass through weight verification stations to ensure each box matches the expected load. Once packed, these boxes are stacked onto pallets using robotic palletizers. These robots follow pre-programmed stacking patterns that balance weight and maximize vertical space without compromising stability. Slip sheets and corner boards are often inserted between layers to protect the boxes during transit. Each completed pallet is then shrink-wrapped using a rotary arm or turntable stretch wrapper, which encases the entire stack in several layers of industrial plastic film to secure the load for transportation. A final barcode label is applied to each pallet, integrating it into the warehouse management system, which tracks every movement of inventory from production to dispatch. Next comes the crucial cold storage phase. The finished pallets are transferred via automated guided vehicles or high-speed conveyor systems into a massive cold storage facility, maintained at a consistent temperature of -18 degrees Celsius or lower. These storage facilities are designed with energy efficiency and inventory management in mind, often featuring high bay racking systems and vertical lift modules that allow for dense, organized storage. Temperature and humidity are monitored continuously by sensors linked to a centralized control room, where technicians receive alerts if any deviations occur. These warehouses are often equipped with backup generators and emergency protocols to ensure uninterrupted refrigeration in the event of power failures. After sufficient time in cold storage, which may range from a few days to several weeks depending on demand, the frozen chicken pallets are scheduled for distribution. The dispatch process begins with a pick and pack phase, where orders from various KFC regional hubs or franchise warehouses are collated. Advanced logistics software optimizes which pallets to pull based on freshness, production date, and delivery location. Selected pallets are loaded onto refrigerated trailers that maintain a controlled environment throughout the entire journey. These trucks use insulated walls and powerful refrigeration units that can be monitored remotely to ensure temperature compliance from factory to franchise. As these trucks transport the frozen chicken to regional KFC distribution centers or directly to individual restaurants, the cold chain is never broken. The receiving locations are equipped with cold storage facilities of their own, ensuring the chicken remains at safe temperatures until it's needed. At this stage, each restaurant receives a specific allocation based on forecasted customer demand, which is calculated using advanced demand planning software linked to point-of-sale data and regional market trends. The chicken remains sealed until it's ready to be used in the restaurant's kitchen, where the final stages of cooking take place. But now it's time to dive into the heart of the KFC restaurant kitchen, where the transformation from pre-cooked frozen chicken into the hot, crispy, golden brown pieces we all recognize occurs. After thawing in temperature-controlled refrigeration units for a specific number of hours, typically overnight, the chicken is brought to the breading station. Though the chicken was par-fried and breaded at the factory, a second layer of fresh breading is applied in-store to create the distinctive double crunch texture KFC is famous for. This is where the Colonel's proprietary 11 herbs and spices come into play. Each restaurant receives sealed tubs of this secret seasoning blend, pre-measured and tamper-proof. The thawed chicken pieces are first dipped into a cold, seasoned egg wash or a specialized batter mix, depending on the region. Then, they are placed into large breading bins containing the flour and spice mixture. Trained team members follow a specific press and fold technique, which involves pressing the flour onto the surface of the chicken and folding it multiple times to ensure full adhesion and the formation of the characteristic craggy, crispy coating. Each piece is then gently shaken to remove excess breading and laid out on wire racks to rest before frying. This resting period is short but essential. It allows the coating to set and adhere to the surface of the meat, reducing slippage during frying. Next, the chicken is placed into large open fryers filled with high-stability frying oil, often a soybean or canola blend, optimized for high temperatures and neutral taste. The fryers are preheated to exact temperatures, typically around 170 to 180 degrees Celsius, and the chicken is cooked under pressure for a controlled duration. KFC's use of pressure fryers is a distinctive element of its cooking process. The pressure cooking not only reduces cooking time, but also seals in moisture, ensuring the chicken remains juicy while achieving a perfectly crispy exterior. Sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration down to the second. Once the timer signals completion, the fryer basket lifts automatically, and the cooked chicken is removed using heat-safe tools to ensure safety and hygiene. After frying, the chicken is transferred to heated holding cabinets that maintain a precise internal temperature, typically around 60 to 65 degrees Celsius, for a limited time, usually no longer than 90 minutes, to ensure optimal freshness and food safety. These cabinets are fitted with internal timers and alert systems to prompt kitchen staff when a batch is nearing the end of its holding time. Any product not sold within this window is discarded according to food safety protocols to maintain KFC standards. Now that the chicken is hot, crisp, and ready, it's portioned into the familiar red and white striped buckets. Each bucket is made from food-grade, grease-resistant cardboard, printed with high-resolution branding that remains vibrant, even under heat and oil exposure. The buckets are assembled on-site from flat pack form using pop and lock mechanisms and lined with waxed paper liners. The kitchen crew follows strict guidelines when arranging the pieces inside each bucket, ensuring an appealing visual mix of drums, thighs, wings, and breasts. The buckets are then sealed with fitted plastic or cardboard lids to retain heat and are either handed to walk-in customers or packed into thermal delivery bags for transport. The final stretch of the production process involves a complex web of quality assurance protocols, food safety audits, sustainability initiatives, and continual technological improvements, all of which are critical to ensuring that every KFC fried chicken bucket, whether purchased in Tokyo, New York, or Johannesburg, meets the same high standard of taste, appearance, and food safety. These behind-the-scenes systems may not be visible to the end consumer, but they represent the foundation of KFC's global manufacturing and supply chain model. One of the most rigorous systems in place is the Hazard Analysis and Critical Control Points, or HACCP, framework. This is applied across all phases of the production lifecycle, from live animal handling at the poultry farms to final packaging at the restaurant level. Every critical control point is identified, monitored, and logged digitally. For example, in the chilling process, sensors verify that the internal temperature of chicken pieces drops to below 4 degrees Celsius within a very specific time frame. If any batch fails to meet that requirement, the system will automatically flag the anomaly, prevent further processing, and isolate the affected lot until a manual inspection is completed. These digital controls are complemented by human oversight. Trained quality control technicians regularly inspect samples at random, visually assessing breeding adhesion, meat color, texture, and aroma. At the plant level, sanitation is treated as a mission-critical activity. Every line, blade, and conveyor is cleaned on a strict schedule using a validated multi-step process that includes rinsing, application of food-grade alkaline and acidic detergents, hot water sanitizing, and ATP testing to detect any microbial residues. Cleaning in place systems are used in closed-loop systems like marinade blenders and oil filtration units, ensuring deep sanitation without the need for dismantling complex machinery. Swabs are taken from surfaces and air samples collected to detect airborne pathogens, all analyzed in on-site microbiological labs. If even a trace of Listeria, Salmonella, or E. coli is detected, entire zones of the plant are shut down and sanitized before production can resume. In parallel to these food safety systems, sensory panels and culinary scientists at centralized R&D hubs conduct organoleptic tests to ensure product consistency. These tests assess everything from the crunch of the breading to the juiciness of the meat and the aroma released when the bucket is first opened. Chicken from multiple plants is cooked and compared side by side in blind taste tests to identify deviations in flavor or texture. If a factory's output strays from the baseline profile, its formulations and techniques are reviewed. In some cases, regional adaptations are permitted. For instance, a slightly spicier breading formula in Southeast Asia, or a less salty blend in Scandinavian markets. But these must be approved through corporate sensory panels and extensive pilot runs. Now it's time to take a look at how traceability and supply chain visibility are achieved at scale. Every piece of chicken can be traced through a blockchain-based system that logs data from farm to fryer. RFID tags and barcode labels track each pallet, batch, and case throughout its journey. When a truck departs a cold storage warehouse, its GPS location is monitored in real time, and its refrigeration status is transmitted back to the operations center every 5 minutes. If a delivery truck's temperature rises above the acceptable range for more than 10 minutes, alerts are sent automatically, and corrective actions are triggered, either rerouting to a nearby cold facility or discarding the load, depending on the severity of the excursion. Once the product reaches the restaurant, the store-level staff become the final link in the quality chain. Every team member is trained not just in food preparation, but in safe handling and equipment calibration. They measure oil temperatures with infrared thermometers before every cooking cycle, check holding cabinet thermostats each hour, and perform timed inventory rotations to prevent expired stock from being used. Any discrepancies are flagged in a digital checklist that is reviewed daily by shift supervisors and weekly by regional managers. Corporate auditors also perform unannounced inspections using checklists derived from international food safety certifications, such as ISO 22000 and BRC Global Standards. But up next is a growing area of emphasis for KFC's manufacturing process, sustainability. As environmental concerns increasingly shape consumer expectations and regulatory policy, KFC and its supply chain partners have invested heavily in reducing their environmental impact without compromising efficiency or food safety. For instance, many factories now operate on hybrid energy models that integrate solar or wind power into the grid supply. Heat exchangers capture and recycle waste heat from fryers and ovens to preheat water for cleaning cycles. Water treatment plants have been installed adjacent to major facilities to purify and reuse water from scalding tanks and chilling baths, thereby reducing freshwater consumption by up to 60%. Waste management is another cornerstone of sustainable operations. Offcuts, bones, and organ meats removed during the evisceration process are rendered into protein meal for use in animal feed or fertilizer. Oil used during the par-frying phase is filtered multiple times and eventually recycled through third-party processes into biodiesel or industrial lubricants. Even the breading flour that falls off during coating is collected, sifted, and reused within the same batch cycle if it remains uncontaminated thanks to high-speed sifters and air classification systems. Packaging materials are continuously redesigned to reduce plastic use, and many regional markets have adopted compostable or recyclable buckets made from sugarcane fiber or recycled cardboard. Now let's touch on automation and the future of food manufacturing. KFC's supply chain continues to push the boundaries of factory automation. Smart robotics now handle everything from chicken loading and cutting to box folding and pallet stacking. Machine learning algorithms analyze yield patterns, worker performance, and maintenance schedules to optimize output while minimizing downtime. Vision systems are paired with artificial intelligence to assess product quality in real time, not just based on weight and shape, but also by identifying anomalies invisible to the human eye, such as microfractures or uneven breading density. One of the most promising developments is the integration of digital twins, virtual replicas of entire production lines that allow engineers to test modifications in real time before applying them in physical factories. If a new breeding formula is under development, it can be modeled digitally to predict how it will behave under tumbling, par-frying, and freezing conditions. These simulations save weeks of trial and error testing and reduce waste. Some facilities even employ predictive maintenance systems powered by sensors embedded in critical equipment. These sensors monitor vibration, temperature, and pressure, allowing for preemptive repairs before machinery fails, ensuring smooth operations and uninterrupted chicken production. KFC has also begun exploring vertical integration of its logistics chain. In some regions, specially designed micro-factories are situated closer to major urban centers, reducing transit time and carbon emissions. These micro-factories handle final stage breading and par-frying, enabling fresher product delivery and enhanced responsiveness to demand fluctuations. Combined with real-time sales analytics from thousands of KFC restaurants, these decentralized production nodes can respond dynamically, ramping up or down based on foot traffic, promotions, or seasonality. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, The truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count or ATP bioluminescence test evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 liters in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids, before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the dearation stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Dearation also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Dearation is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a 2-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses: never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction